from Professor Harvey Reall from Cambridge University, and he's going to talk us about some recent development in strong cosmic censorship. So yes, you have 40 minutes, and whenever you're ready, you can start. Thank you.
Okay, well, thank you very much to the organisers for putting this nice event together. So they've asked me to talk about strong cosmic censorship, which is a question about what happens inside black holes. And it's going to be a fairly selective talk, so I'll review the general idea and then move on to some recent developments in the subject that I've been involved with, which you can find described in these papers written with my collaborators, Oscar Diaz, Felicity Eperon and George Santos. The ones in bold are probably the best ones to look at because they have more pedagogical introductions. So here's an outline of the talk. So the first half of the talk will be a review of what we know about strong cosmic censorship with zero cosmological constant. And then I'll come to the recent work which concerns violations of strong cosmic censorship when the cosmological constant is non-zero. And then at the end, I will describe two possible ways of rescuing strong cosmic censorship in these situations. So let's start with a review of what is strong cosmic censorship. So let's start with lambda equals 0, and we have the famous Reissner-Nordstrom or Kerr black holes. And here's a Penrose diagram for Reissner-Nordstrom, asymptotic null infinity over here, and then the black hole event horizon here, white hole horizon here. So this is the region outside the black hole. This is the region inside the black hole. And then we've got the other asymptotically flat region over here, and the white hole region here. The interesting thing about Reissner-Nordstrom or Kerr is that as well as the event horizon, these solutions can be smoothly extended across this horizon in blue here, which is inside the black hole. And what's striking about this is that in fact there are infinitely many ways of doing this. So there's not a unique extension across this horizon. There are infinitely many ways of smoothly extending these solutions across the horizon, which are consistent with the equations of motion. And so what that means is that if we were to consider the initial value problem here, where we prescribe initial data on a surface like this sigma, which goes from one spatial infinity to another, even if we know that the initial data here is exactly Reissner-Nordstrom or exactly Kerr, then all we can say is that the solution is exactly Reissner-Nordstrom or Kerr up to this inner horizon. But once we go beyond that, we don't know that the solution, we don't know what the solution is. There are infinitely many ways of extending it. And so there's a lack of predictability or lack of determinism in the initial value problem in classical general relativity. Even if we know the initial data exactly, we can't predict what happens once we go beyond this horizon. So this horizon is a boundary to the uniqueness of the Cauchy problem, and so we call it a Cauchy horizon. Now, when you first study these solutions, you may not learn about this non-uniqueness when you go into this region, and that's because often people impose extra assumptions on the solution, such as analyticity or spherical symmetry. But really, you shouldn't be adding extra assumptions. You should just be prescribing initial data, evolving it, and see what you get. And if you do that, there are infinitely many ways of going into this region here. So this is the Penrose diagram for a maximally extended two-sided black hole. If you consider a black hole which is formed from collapse, then instead of this double null surface, you get just a portion of null surface down here. You get an early time portion of this right-hand component of the Cauchy horizon. So a lot of what I'm going to be saying is really focusing just on this early time portion of the Cauchy horizon, because that's what's present in gravitational collapse. Okay, this was first noticed long ago by Roger, and he also identified a possible way out for this worrying lack of determinism, which is that maybe this Cauchy horizon is unstable. So here's the usual heuristic argument we use to explain that. So this region here is the region outside the black hole, and we have an observer, Alice, who's immortal. She lives forever, so her world line ends at time like infinity. Bob is more adventurous. Bob has jumped into the black hole, and he's going to try and cross the Cauchy horizon and see what happens there. Every second, Alice sends a signal to Bob, which are these lines in purple here. And because Alice lives forever, she sends infinitely many signals, and we see that Bob receives an infinite number of signals as he crosses the Cauchy horizon. So the frequency of those signals is clearly diverging there. There's an infinite blue shift, And so that strongly suggests that when we consider the gravitational back reaction of this, then that's going to cause a large effect on the geometry here. And so what this argument suggests is that maybe small perturbations in this region outside the black hole can have a very large effect near the Cauchy horizon, and perhaps to the extent that they destroy it, and when rescue determinism, if the destruction means that the space-time ends at a singularity, for example. So to formalize this as a conjecture, the strong cosmic censorship conjecture says that if we consider complete asymptotically flat initial data for the Einstein-Maxwell equations, then generically the resulting solution cannot be extended across a Cauchy horizon. The key word here being generically. The idea here is that Reissner-Nordstrom or Kerr are non-generic solutions. So they have Cauchy horizons, but if you slightly perturb them, then the perturbed solution would not have a Cauchy horizon. And this is quite appealing because if it's correct, then this conjecture restores predictability without invoking any kind of poorly understood physics, such as, for example, the back reaction of quantum effects. So what evidence is there in favor of this conjecture? Well, this has been something people have studied for several decades. The first thing people look at is linear perturbations of black holes. So let's think about linear perturbations of Reissner-Nordstrom, for example. And this could be either massless scalar field or linearized coupled gravitational and electromagnetic perturbations. So for simplicity, let me just focus on the massless scalar. And let's take initial data for our perturbation, which is compactly supported on this initial surface here. So we have our initial surface, we turn on some scalar field over here, for example, we evolve it, and we want to ask what happens. So what happens is that we know that in an asymptotically flat space-time, perturbations outside the black hole will decay, but they do so quite slowly. They exhibit power law decay. So this is what's known as a late time tail. And this fairly slow decay outside the black hole is slow enough to trigger this blue shift instability that I discussed earlier at the Cauchy horizon. With the result that at the Cauchy horizon, the gradient of the scalar field diverges, and therefore the energy density measured by an observer who crosses the Cauchy horizon is also divergent there. And therefore, this is in agreement with the picture that we would expect a large back reaction on the metric there. So the study of linear perturbations is in agreement with the conjecture. What about nonlinear? So this was first studied in the early 90s by Poisson and Israel. So going nonlinear is hard. So they cooked up a toy model where they considered Reissner-Nordstrom, and they coupled the Einstein-Maxwell equations to a kind of very simplistic form of matter, which they call null dust. So this is pressureless matter which moves along null geodesics. The nice thing about this is it's quite a tractable model to study, and they were able to show that in this model, when they perturb a Reissner-Nordstrom black hole, the back reaction causes the Kretschmann scalar to diverge at the Cauchy horizon. And so the Cauchy horizon therefore becomes singular in agreement with the strong cosmic censorship conjecture. However, there was something that was noted early in the 90s, was that although the Cauchy horizon becomes singular, so the metric is not C2 there, you can still continuously extend the metric across the Cauchy horizon. So there still exists a C0 extension of the metric there. And in particular, this means the Cauchy horizon can still be defined. And what this implies is that the singularity inside the perturbed black hole is null, at least at early time. And this is in disagreement with perhaps what people expected before this, which is that when you perturb the black hole, the singularity that formed would be like a Schwarzschild singularity, in other words, a space-like singularity. But in fact, it turns out that it's null, at least at early time. So more recently, in the last couple of decades, mathematicians have got interested in this problem, and they've proved lots of rigorous results about this. So let's look at Reissner-Nordstrom, and let's look at take the Einstein-Maxwell equations. And it would be nice to impose spherical symmetry, because that makes things tractable. But of course, we have Birkhoff's theorem, which says there's no dynamics in spherical symmetry. So let's evade that by including an extra scalar field, an uncharged scalar field. And so we're going to consider Einstein-Maxwell coupled to this scalar field. And we can use this scalar field to study nonlinear perturbations of Reissner-Nordstrom. So what's been proved by, notably by de Fermos and then by Luc and O, is that if you do this, if you perturb Reissner-Nordstrom by this scalar field, so we're considering small but nonlinear perturbations, then the resulting perturbed solution can be continuously and globally extended across the Cauchy horizon, and that the extension is not C2 at the Cauchy horizon. So let me show in pictures what that means. It means we have initial data on sigma, where we turn on some scalar field to perturb the black hole. We then evolve it. And what's been proved is that in the resulting space-time, the Penrose diagram looks exactly like this. We can extend continuously across a Cauchy horizon, but the extension is not C2, so the curvature diverges at the Cauchy horizon, which is therefore a globally null singularity. So it's quite striking that the singularity here is everywhere null. It is space-like nowhere. So quite a surprise considering the earlier expectations that it would be like a Schwarzschild singularity. So there's a null singularity everywhere inside the black hole. That was for Reissner-Nordstrom, and similar results are expected for perturbations of Kerr by gravitational perturbations. Okay, so the Cauchy horizon, when we perturb it, becomes singular in agreement with the conjecture. So that seems to rescue the predictability, but actually things are not quite so straightforward. Again, in the early 90s, Amos Ori noticed where he asked what happens if we consider the experience of an observer who approaches this singular Cauchy horizon. So of course, there's a curvature singularity there, which means that tidal forces diverge at this Cauchy horizon. But from the point of view of the observer, it's not so much the pointwise divergence of tidal forces which is important. It's more the integrated effect of those tidal forces. So what is the total tidal distortion experienced by the observer? In other words, the integrated distortion. And so Ori observed that this can remain bounded. And so therefore the question comes back, well, what happens to an observer who approaches one of these singularities, that they're not necessarily destroyed because the total distortion can be finite? So to answer this question of what happens, we need to say more about what this observer is made of, what their equations of motion are, and if the equations of motion for the matter fields that comprise the observer still make sense at the Cauchy horizon, then we're back to the original problem. We still have a problem with determinism because we would still be able to extend beyond the Cauchy horizon consistently with those equations of motion. So what does it mean to make sense at a singularity? So the point is that we can make sense mathematically of solutions which are less regular than C2 as so-called weak solutions of the equations of motion. So this is a very well established idea in mathematics, but it's also very relevant physically. So for example, if you consider a compressible perfect fluid, it's well known it can form shocks, and shocks are described as weak solutions of the compressible Euler equations. So we want to ask, well, what does it make sense? Can we talk about weak solutions in the context of the Einstein equation? And we can. So the criterion to have a weak solution of the Einstein equation is that the Christoffel symbols should be locally square integrable in some chart. So that's the notion of weak solution that applies to the Einstein equation. So armed with this, we can present the modern version of the strong cosmic censorship conjecture, which is due to Christodoulou. So Christodoulou's version says that generically, it is not possible to extend across the Cauchy horizon with locally square integrable Christoffel symbols. Okay, so this is very appealing because if it's correct, it means that generically there is no way of extending beyond the Cauchy horizon in such a way that the equations of motion are satisfied there, even in a weak sense. And so determinism is restored. So this version is stronger than what I'll call the C2 version of strong cosmic censorship, or the physicist version, which would be the statement that generically no C2 extension exists. So it's a stronger version of the conjecture, but it's still believed to be true for lambda equals 0, although it has not yet been proved. Okay, so now I can come to the recent story. So now let me introduce a cosmological constant. So let's first look at positive lambda. So the new feature with a positive cosmological constant is we now have a cosmological horizon. So that's in orange here. So this region here, region 1, is between the black hole horizon and the cosmological horizon. If we go through the cosmological horizon, we reach a region with the space-like infinity of de Sitter space. And then there are all the other regions that we expect to see. And up here, region 2 is the black hole region. And if we consider a Reissner-Nordstrom or a Kerr-de Sitter black hole, then just like their lambda equals 0 counterparts, we have a Cauchy horizon, and these solutions can be smoothly extended across the Cauchy horizon in infinitely many different ways, all consistently with the equations of motion. So the problem is still there with determinism. So let's now rerun this heuristic argument for the instability of the Cauchy horizon, but now in the de Sitter setting. So again, I've just drawn my two regions, the region outside the black hole, region inside the black hole. Alice is again outside the black hole, sending signals to Bob, who's crossing the Cauchy horizon. I've probably drawn Alice's world line in the wrong place here. I should really have drawn it ending up here at time like infinity. So imagine this line ends up here. So again, Alice is sending signals to Bob. And again, you see the signals of this infinite blue shift at the Cauchy horizon. But now there's a new feature, which is that Alice is living in this de Sitter space, which is expanding exponentially with this cosmological horizon. And so the signals that Alice is sending are having to climb out of this potential well associated with the cosmological horizon. And so they're suffering a redshift. So although we have this blue shift over here, we have a competing redshift outside the black hole. So the question is now, which effect wins? So you can see that in de Sitter space, it seems likely that this Cauchy horizon instability is going to be weaker than it was in the asymptotically flat context. So it turns out that for a de Sitter black hole, the late time decay of linear perturbations outside the hole is determined by quasi-normal modes. So remember, quasi-normal modes are the damped oscillations of the black hole. So if we know the quasi-normal modes, we can define a quantity called the spectral gap, which is, it's defined as follows: consider all the quasi-normal modes and then look at the one with smallest imaginary part, in other words, the slowest decaying quasi-normal mode. And so the imaginary part of that mode is basically the spectral gap. So the point of this is that generic perturbations decay exponentially in time as e to the minus alpha t, where alpha is the spectral gap. So this is outside the black hole. We have this exponential decay in de Sitter space. So this is qualitatively different from what happened for lambda equals 0, where for lambda equals 0, we had these late time tails, which gave us power law decay. Here we have much faster decay, exponential decay, and that's coming from the exponential de Sitter expansion outside the black hole. So if this is how perturbation behaves outside the black hole, we can ask, what consequences does that have for how it behaves inside the black hole near the Cauchy horizon? So if we introduce Kruskal coordinates so that the Cauchy horizon is at v equals 0, then if you work out how generic perturbations behave near the Cauchy horizon, it goes like minus v to the power beta. So I'm assuming v is negative in the black hole region, where beta is defined as alpha, the spectral gap, divided by kappa minus, which is the surface gravity of the Cauchy horizon. In other words, it's the decay rate of the slowest quasi-normal mode divided by the surface gravity of the Cauchy horizon. So just looking at this function, you can see that the gradient of this will blow up if beta is less than 1. So the energy density of the perturbation will blow up if beta is less than 1. And so that would be evidence in favor of the C2 version of strong cosmic censorship, where we'd expect a curvature singularity to form at the Cauchy horizon, if that were the case. And this is not square integrable if beta is less than 1/2. So if beta turns out to be less than 1/2, that would be evidence in favor of this Christodoulou version of strong cosmic censorship, the one that says we can't even make sense of the equations of motion weakly at the Cauchy horizon. So the question is, what is this value of this quantity beta? Is it less than 1? Is it less than 1/2? What is it? And you see that to calculate beta, we need to consider all the quasi-normal modes and figure out which one is lowest. Okay, so it's a slightly tricky problem. This was only done quite recently, to good accuracy by Vitor Cardoso and collaborators. So they did a careful numerical study of massless scalar field quasi-normal modes for Reissner-Nordstrom-de Sitter. And what they found is that, well, far from extremality, beta is less than 1/2, and so all the versions of strong cosmic censorship are respected. But near extremality, beta is between 1/2 and 1, which means that the massless scalar field perturbations violate this Christodoulou version of strong cosmic censorship, but not the C2 version of strong cosmic censorship. Or in words, it means that they point to a picture where the curvature will blow up at the Cauchy horizon, but you can still extend beyond the Cauchy horizon in such a way that all the equations of motion still make sense there. And so there's still a problem for predictability. This is all linear, but there's numerical confirmation that this is true even when you go nonlinear and includes some back reaction. Okay, so what I can describe what we did now. So the work I just described was for a scalar field. What we did is we looked at perhaps a more physical case where we don't include a scalar field, and we just look at gravitational and electromagnetic perturbations of Reissner-Nordstrom-de Sitter. And we found something much worse in this case. So in this case, we find that near-extremal Reissner-Nordstrom-de Sitter black holes always have beta bigger than 2. So that means that in pure Einstein-Maxwell theory, not only is this Christodoulou version of strong cosmic censorship violated, but so is the C2 version. In other words, near extremality, a curvature singularity does not form at the Cauchy horizon. The instability is not strong enough. And in fact, it's worse than that. So generic perturbations are CR, R times continuously differentiable at the Cauchy horizon, where R can be made arbitrarily large by making the black hole sufficiently near extremal and sufficiently large in units of lambda. So you can violate strong cosmic censorship as badly as you want in pure Einstein-Maxwell theory by considering large near extremal black holes. You can make the behavior at the Cauchy horizon as smooth as you like. So this is a bad violation of strong cosmic censorship for positive cosmological constant. Well, okay, so this is interesting because lambda positive is, of course, the real world. But on the other hand, near extremal Reissner-Nordstrom-de Sitter is not the real world because highly charged black holes don't exist in nature, as far as we know. But of course, Reissner-Nordstrom is often regarded as a toy model for Kerr. So the question is this evidence or is it suggesting that there should also be a violation of strong cosmic censorship for near extremal Kerr-de Sitter, which of course is a very physical solution. So this was something else we looked at. And in this case, as I said, to calculate this parameter beta, this was, remember, we had to calculate all the quasi-normal modes, find the one with the smallest imaginary part, and then divide by the surface gravity of the Cauchy horizon. Using geometric optics, we can get an upper bound on the decay rate of the lowest quasi-normal mode. And using that approach, we were able to show that for Kerr-de Sitter, beta is always less than 1/2, with this inequality being saturated in the extremal limit. Now remember, beta equals 1/2 was the critical value for Christodoulou's version of strong cosmic censorship, the physical version or the strongest version of interest. And so this means that for Kerr-de Sitter, strong cosmic censorship is respected. So when we perturb Kerr-de Sitter, then generically you cannot extend across the Cauchy horizon in any way so that the equations of motion make sense there. Okay, so it's in full agreement with this physical version of strong cosmic censorship. So we seem to be in this peculiar situation for positive lambda, where strong cosmic censorship is respected by pure Einstein gravity, but is violated in Einstein-Maxwell theory, which is rather surprising. Good. Okay, so that was positive lambda. I'll come back to that in a few minutes. Let me now say something about negative lambda. So for negative lambda, the decay of linear perturbations of a black hole is governed by quasi-normal modes, just as for positive lambda. But the interesting thing in anti-de Sitter, at least in 4 dimensions and higher, is that the quasi-normal modes, if you consider quasi-normal modes with larger and larger angular frequencies, the decay rates of those quasi-normal modes go to 0. So that means that the spectral gap of an anti-de Sitter black hole, at least in 4 or more dimensions, is 0. So it seems that, so in other words, you have a very, very slow decay in de Sitter space. So it's really anti-de Sitter space. So de Sitter had faster decay, anti-de Sitter has much slower decay than asymptotically flat space. So in fact, it goes like a reciprocal of a logarithm of the time, something like that. So you might expect that the fact that the decay in ADS is much slower than in asymptotically flat space would lead to a strengthened instability of the Cauchy horizon, because if the perturbation outside the black hole is decaying more slowly, then it's got longer, it's just hanging around longer to trigger this blue shift instability at the Cauchy horizon. And so since we expect the Christodoulou version of strong cosmic censorship to be true for the lambda equals 0 case, it's even more likely to be true for negative lambda. In fact, you might even wonder whether with negative lambda, the instability of the Cauchy horizon is strong enough to prevent even a C0 extension across the Cauchy horizon. Could it be strong enough to in fact do something like turn the singularity into something like Schwarzschild, something space-like? Surprisingly, perhaps the evidence that we have suggests that that's not the case, and that at least for Reissner-Nordstrom ADS, it's been proved that there is still a continuous extension across the Cauchy horizon. For Kerr ADS, things get very weird, and whether or not you have such an extension depends on some number theoretic properties of the black hole parameters. So this is all very recent work of Christoph Kahler. I can say more about that in the discussion if anyone wants to know more. So this was negative lambda in 4 or more dimensions. Let me tell you what we did with negative lambda, which was to go down to 3 dimensions. So in 3 dimensions, there's a well-known analog of the Kerr ADS solution called the BTZ black hole. And so that has a qualitatively similar properties to Kerr ADS. It has a Cauchy horizon. And so one can look at perturbations of BTZ and ask what happens. So we looked at lots of different kinds of perturbations of BTZ, scalar fields, massive vectors, massive spin 2, anything you want to think of. And what's interesting about the 3-dimensional case is that you don't have this slow decay. In higher dimensions, this slow decay of quasi-normal modes can be related to a behavior of null GD6 for anti-de Sitter black holes, which is that they exhibit a phenomenon called stable trapping. So photons around anti-de Sitter black holes can orbit the black hole stably at large distance from the black hole. That doesn't happen in 2+1 dimensions for the BTZ black hole, and that's why you don't get this slow decay phenomenon. And so for BTZ, linear perturbations decay exponentially fast, just as we found for Reissner-Nordstrom-de Sitter, or Kerr-de Sitter. So the criterion for the Christodoulou version of strong cosmic censorship to be respected is beta less than 1/2, just as for positive lambda. So by looking at quasi-normal modes and calculating beta, we can answer the question of whether or not strong cosmic censorship is respected. And our result is that for any type of perturbing field, we can make beta as large as we want by taking a black hole close enough to extremality. And so the picture is very similar to the story we had for Reissner-Nordstrom-de Sitter, which is that we can make strong cosmic censorship is violated. The behavior of the Cauchy horizon can be made arbitrarily smooth by considering a black hole, which is sufficiently close to extremality. This, of course, is all linear, but there's been some recent numerical work by Franz Pretorius and his students who've confirmed that nonlinearity does not change this conclusion. Okay, so we've seen 2 bad violations of strong cosmic censorship. We've seen it's violated for Reissner-Nordstrom-de Sitter and for BTZ. Is there any way out? Is there any way of rescuing the strong cosmic censorship conjecture and restoring predictability to classical physics? So I'll describe 2 ways out. The first is classical, the second is quantum. So let's start with the classical. So let me highlight something we've assumed so far, which is that whenever I've discussed perturbations of black holes, I've always assumed that they arise from smooth initial data. So the initial perturbation is always assumed to be smooth. So recently, De Fermos and Schlappentock-Rothman suggested that maybe we should enlarge the space of admissible initial data and allow rough initial data, so initial data which is not smooth. If you do that, then it's no longer the case that the late time behavior is dictated by quasi-normal modes, and so one has to revisit the problem. So what you can see very easily, there's a very simple argument for this, is that when you allow rough initial data, the smoothness of the solution in the technical sense of Sobolev spaces generically gets worse at the Cauchy horizon. So that as when you evolve the initial data, you start off with rough initial data. When you evolve it, it's rougher at the Cauchy horizon than it was initially. So that means that if you start off with some generic perturbation from initial data which has the minimum acceptable level of smoothness, which could be determined either physically or mathematically, for example, by the requirement of well-posedness of the Cauchy problem. If you evolve that initial data with minimum smoothness, then when you reach the Cauchy horizon, it will no longer have the minimum acceptable level of smoothness. And so that therefore would give you a way out for strong cosmic censorship if you're willing to contemplate rough initial data and rough perturbations. The argument is very robust, and in fact, it only really relies on one thing, which is an inequality between the surface gravity of the Cauchy horizon and the surface gravity of the event horizon. So kappa minus is always greater than kappa plus. So this holds for Reissner-Nordstrom-de Sitter. It also holds for BTZ. So this actually applies to either of the counterexamples to strong cosmic censorship I've discussed. And in fact, all the black holes I've looked at satisfy this inequality. So there must be some reason for this inequality. And I've suggested to various masters and PhD students, and they try and figure out why this is true. So far, no one's taken up my offer, but I think it's an interesting question to understand when this is true, for what kind of matter model, for example, would guarantee this. Okay, so that's one way out for the conjecture, which is to allow rough data. Let's now turn to another way out, which is to invoke quantum effects. So for Reissner-Nordstrom-de Sitter or BTZ, we can ask, do quantum effects help? So if we consider quantum fields in curved space-time, even if we consider a very symmetrical state, such as the Hartle-Hawking state, the expectation value of the energy momentum tensor is still non-zero. So this is called vacuum polarization. And so this is going to back react on the space-time geometry through the semi-classical Einstein equation. And the question is, could that have the effect of destroying the Cauchy horizon and rescuing strong cosmic censorship? So this was looked at long ago for a two-dimensional toy model. In 2 dimensions, it's very easy to calculate this using conservation laws. And indeed, in 2 dimensions, you find that this diverges at a Cauchy horizon. So if this 2-dimensional behavior also extended to 3 or 4 dimensions, then this would be, could this be enough to rescue strong cosmic censorship? So the question is there a divergence like this also for BTZ or for Reissner-Nordstrom-de Sitter? And if there is a divergence, is it strong enough to really kill off the Cauchy horizon in the sense that you can't extend beyond it in any sense compatible with the equations of motion? So the first answer to this is to look at this for BTZ, which is what we did in our paper. So for BTZ, it's a sufficiently simple solution that you can calculate the expectation value of the energy momentum tensor for a scalar field explicitly, at least for the Hartle-Hawking state, which is the state you'd expect the fields to approach at late time in an anti-de Sitter black hole. And so we can calculate this thing explicitly, and you can see that if you have a black hole which is far from extremality, this does diverge at the Cauchy horizon. But again, if you get close to extremality, this becomes better behaved, and in fact, it's bounded at the Cauchy horizon if beta is bigger than 1. So in other words, for a black hole which is sufficiently near extremal. So in other words, for BTZ, this does not solve the problem. The energy momentum tensor of our quantum field remains bounded at the Cauchy horizon if we're close to extremality. What about Reissner-Nordstrom-de Sitter? This is harder because we're now in 4 dimensions, but nevertheless, it's been solved. So Hollands, Wald, and Zahn last year calculated the expectation value of the energy momentum tensor for a scalar field in essentially in an arbitrary quantum state. And what they found is that near the Cauchy horizon, if we introduce Kruskal-like coordinates so that the Cauchy horizon is at v = 0, then there is a divergence in the expectation value of the energy momentum tensor. and it diverges like an inverse square. So it goes like 1 over v squared. So indeed, the energy momentum tensor diverges at the Cauchy horizon, and it does so pretty badly. This is strong enough in order to that it would ensure that there's no sense in which you could extend across the Cauchy horizon consistently with the equations of motion. So this does seem to rescue the conjecture. This c is a constant which is independent of the quantum state and depends only on the black hole parameters. Generically, it's non-zero. So for Reissner-Nordstrom-de Sitter, then, it looks like the back reaction of quantum fields is strong enough to rescue strong cosmic censorship. So that's an appealing way out. We could also ask, well, if we go back to BTZ, what happens for BTZ from this point of view? It turns out that for BTZ, something very special happens, which is that this constant C just happens to be 0. It's just a very special cancellation that happens for this very symmetrical black hole in 3 dimensions. And so you don't get that divergence in 3 dimensions. So that explains our earlier calculation. However, there is a suggestion for a way out even for BTZ, which is that for BTZ, this is non-zero. It just doesn't diverge fast enough at the Cauchy horizon. Because it's non-zero, there will be some back reaction on the geometry through the semi-classical Einstein equation. And so it's plausible that if you now consider quantum fields on that back reacted geometry, then since you've now deformed the geometry, you'll no longer have C equal to 0. So we'll now have C non-zero. And so this kind of points to the idea that if we go to second order in H bar, then we will see a divergence of the desired strength. And so perhaps second order quantum effects will rescue strong cosmic censorship for the BTZ black hole. So I think that's quite an appealing picture, but the calculations involved in confirming this would be quite horrible. Okay, so let me summarize. So strong cosmic censorship is the idea that classical physics should be predictable from initial data. As I've explained, it's very likely to be true in 4 dimensions with a cosmological constant which is 0 or negative. I've also explained that it's true for pure Einstein theory with positive lambda, for Kerr-de Sitter, but that it's badly violated in pure Einstein-Maxwell theory with positive lambda, so Reissner-Nordstrom-de Sitter, and also in 3 dimensions with negative lambda, so that's the BTZ black hole. I've told you that strong cosmic censorship can be rescued classically if we're willing to enlarge the class of admissible initial data, allowing it to be rough. And at least for Reissner-Nordstrom-de Sitter, and perhaps also for BTZ, quantum field theory effects may save the conjecture. Okay, thank you for your attention.
Thank you for this very interesting talk. So we have time just for one quick question. I think we have one from the attendees. No, we don't have it anymore. There was one hand raised. Okay, maybe someone's shy. So is there one question? Does anyone have a question? So yeah, there is one question in the chat. Aaron had. Maybe I can unmute you. You can ask.
Can you hear me?
Yes.
Great. Yes, I was wondering if I just do linear stability analysis of usual black holes, then I would set up a boundary value problem at the horizon and at infinity. But if I want to investigate the stability of the Cauchy horizon, naively at least, I would set up a boundary value problem between the Cauchy horizon and the usual horizon. So why is that intuition wrong, or can you comment on this?
Well, first thing is you wouldn't impose boundary conditions at the event horizon if you were doing stability analysis of black holes. You want to consider initial data on a slice which penetrated the event horizon, and smoothness at the event horizon should be an output, not an input, right? So you consider initial data which is smooth on this kind of slice and evolve it, and what you get is what you get, right? You shouldn't be imposing boundary conditions here. That would be an output, not an input. Okay, so similarly at the Cauchy horizon, the behavior at the Cauchy horizon is an output, not an input. But maybe what you're asking about is mode solutions. So often when you're doing these calculations, it's very convenient to work with a basis of plane wave or fixed frequency solutions. And you can distinguish different types of mode solution by their smoothness here and here or here and here. And it's true that when you're doing the calculations, you introduce bases and different mode solutions are smooth in different places. But those mode solutions are just there for our convenience in doing the calculations. There's not some physical boundary condition being imposed either at the event horizon or the Cauchy horizon, because, as I said, these should be outputs, not inputs.
Okay, thanks.
Okay, thank you. And yes, there are other questions, but let's postpone them to the discussion session. So thank you, Harvey, for your very nice talk. And let's move to the next speaker, the last speaker of the session.